Welcome to lesson 3 of our second unit here. So stretching and compressing graphs of functions, that's our a value from when we were working with sine and cosine. We're still going to use that same language. So we can see it showing up in our function notation compared to our parent function here. And so in terms of mapping notation, because that a is on the outside of our function, we're going to see it affect our y value. Outside the function means it's impacting our output, which is also known as our y value. So a couple key details is that when we have a fraction or a decimal, so somewhere between 0 and 1, it's going to be a compression. We're going to be squishing our graph downward and upward vertically. If our a value is greater than 1, then it's going to be stretched. And this is true for all absolute values of a. That's why when we talked about amplitude, we always talked about the positive a value, the absolute value of a, because that negative doesn't actually impact our vertical stretch and compression. That negative, as we learned last lesson, is strictly going to reflect it over the x-axis. So in our first example here, it's a really good one to see it because we're working with a parabola. That should be something that's familiar from grade 11. So we see that y equals f of x equals x squared. And that's what's already given to us. The screen is very sensitive. I'm not on my usual device here, so I apologize in advance for any funny business that might happen. We've got y equals 3f of x. So again, that is a, and it is greater than 1, so I know this is going to be a stretch. Okay, so what that means is that for every point that I had in my original graph, what I'm going to do is I'm going to multiply my y value by 3. So you can make a table of values to work with mapping notation, and that's what I'm going to do for this one. Or you can just kind of identify your points and do it mentally, and I'm going to do that for the next example. So I'm going to pause my video here. I'm going to do my work on the side. I'm not going to walk you through it per se, because you've already seen mapping notation in our last couple lessons. So I wouldn't mind if you also pause your video right now to give it a shot on your own. And then when you resume, then the answer will be here and you can check to see how you did. Okay, so we can see that, again, it's just the y value that's going to change. My x values stay the same throughout all 3 of these because I'm only impacting the outside of my function. Here I'm going to multiply by 3. Here I'm going to multiply it by -1/2. So when I go to graph 3f of x, and maybe I'm going to graph it using a different color, to graph it using green, I'm probably not going to even include these points because based on the kind of scale that my graph is at, those are going to be way off up above here. So I just need to worry about -1 and +3, 0 and 0, and 1 and +3. And so we can see this. And when we worked with quadratics, and you probably noticed this last year, make these look pretty even. It looks like it's getting skinnier, but really what we're doing is we're taking this point and we're moving it upwards. So it's a vertical stretch is what we call it. Okay, and so some people would think of it as it's getting narrower, but this is strictly a vertical change. You've still got to be careful that it doesn't look too V-ish. Make sure we still preserve that curve. Okay, and that's 3f of x, or you could call it y1. Going back to blue for the last one. Not only was this compression, but also a reflection. So I've got -2 and 2, -1 and -1/2, 0 and 0. Here, 2 and 2. So again, you might have looked at this parabola last year and been like, oh, it was squished down, and then, but so it got wider. We can only talk about really like one trait at a time, either vertical or horizontal at any given moment. So we would just talk strictly about like if we had taken a piece of, I don't know, cardboard, metal, and pushed up on it and squished it. So it looks fatter, but really it's just vertically compressed. It's kind of my best analogy. Think about like taking a ball of Play-Doh and squishing it. All of a sudden it seems like horizontally it's stretched, but really it's just looks fatter because we've compressed it. So that's how we would graph these guys, and again using mapping notation. And don't forget to label Y2. So example 2, again we're going to see how we can impact this. So going back here, we had an invariant point in that not only for our reflection did 0, 0 not change, that point that's on my x-axis didn't change, but because of my y value being 0, even when I multiply it, that stretch and compression, those points still won't change. So anytime, and you can make this as a note to yourself, or you can just be like, yeah, whatever, Miss Conrad, I'm just always going to make a table of values. Whatever works for you, but anytime y equals 0, that's not going to be impacted by your A. So it will be an invariant point when looking at A. So knowing that, I can identify some invariant points right away in my next graph. I'm going to keep those exactly the same. I'm going to identify some critical points. I'm going to use the same colors that I used in the last video just for some consistency. So I'm going to do a maximum, minimum, maximum here, and I'm going to use those kind of to help me out. So I'm reflecting, and again, I just always like to describe things to myself. So reflect over x, and then I'm going to stretch by 2. If you want to give this a shot, pause the video now. I'm going to pause mine too so I can do it without taking up too much of your time. So I didn't do the mapping notation here. I strictly did it by looking at my value. So my y value here for this critical point was 1, sorry. So when I multiply by 2, now all of a sudden I'm going to be dealing with 2. My critical point here was already at -2, so I reflected it, knew I was working with the positives. And then I said instead of 2, it should be multiplied by 2, so that's 4. Same thing happened here. 2 reflected and multiplied by 2. Again, trying to preserve the same kind of shape, the fact that it changes kind of what the concavity of it looks like. This one was less concave than this parabola-esque part. So just kind of bearing all those characteristics of the graph should remain the same whether or not we've stretched or compressed it at all. So again, we're looking at example 3. Here, again, we're reflecting over x, and then this time we are compressing. So we're gonna make it kind of less vertical. So again, try and pause the video, and you can kind of give it a shot on your own. I'll talk through this one, so if you didn't do well on that previous one on your own, you can just keep following the video. My first thing again is always identifying my critical points and invariant points. So I'm going to just choose a 2. Anytime my graph changes direction really is when I'm going to choose my critical points, and invariant points, like we said on the previous page with respect to our A value, are going to be anything that hits the x-axis because y is 0, so multiplying by anything would still result in 0. Once I've identified those, now I can start putting my new points on. So I'm going to reflect over my x-axis, and then I'm going to take it by half. So where I was at +1 originally, I'd go to -1, and then I go, actually it's -1/2. Same thing happens here. It's nice in a flat line, so I'm going to get the same value. Okay, I was at +3, so I go to -3, and then half of -3 is 1.5. invariant point stays the same. That's its name. The last one I'm at -3, so I go up to +3, take it to half. And now I can connect my points. There we go. Again, I don't put arrows on the end because my graph originally didn't have arrows on the end, and that's okay. I'm going to name this Y1. So I forgot to name the last one. It should have been Y1 down here. So that's vertical stretching and compressing. Horizontal stretching and compressing, as you may have already noticed, anytime we're impacting our inside of our function, it seems to kind of have an opposite effect. So when we're looking at y equals f of b times x, in comparison to my parent function, what's going to happen is that I take my parent function points for mapping notation and I'm dividing by b. So again, doing the opposite operation. So just like with our horizontal shifts, when it looks like it's adding, you really subtract and shift left. Same thing happens here. So we go to example 4 and we see, okay, well, the original function is here, and that's great. We can then look at this and say, okay, well, b is a half. Well, based on the descriptions up here, when b is between 0 and 1, because we do the opposite, or we're dividing by a half, that's really like multiplying by 2. We're saying how many halves are there. So like multiplying by 2, that means that we're actually going to stretch by a factor of 1 over b. So I'm going to look at my denominator in this case, or we can think of it as a stretch by 1 over 1/2. And if we look at it like that, well, dividing by a fraction is like multiplying by the reciprocal. So it's like 1 times 2 over 1. Well, that's the same as just 2. So that's 2. That's my stretching factor horizontally. So if horizontal stretches or vertical stretches give me invariant points on my x-axis, I can anticipate that I'm going to have vertical stretches or horizontal stretches. My invariant points will be on my y-axis, because that is where x equals 1 or 0, sorry. And so multiplying it by anything is going to have no impact. I'm going to do mapping notation here again, just to make sure that we're comfortable with that kind of idea. If you want to follow along, you can. If you want to pause the video and then skip ahead, I won't be offended because I won't know. So my original function is going to be f of x, and I'm going to choose some points. So I've got -1 and 0. I've got a maximum at 0 and 2. And I've got another 0 at 1 and 0. Minimum at 2 and -2. And finally, my graph ends at 3 and 0. So if that's f of x, then when I go to do y1, I am going to multiply by 1 over b, or that stretch factor of 2. So I'm going to go -1 times 2 is -2. Y is unaffected because, again, b is inside the function, so we're changing our x value. It's inside the function, affecting the input, which is x. 0 times 2 is still 0, which again is y, that's an invariant point. 1 times 2 is 2. 2 times 2 is 4. And 3 times 2 is 6. Okay, so automatically I'm seeing that these values become much, much bigger for my x. Which was a little disconcerting, honestly, as I'm doing it, because I don't even think that that's really going to fit on my graph. Like if I put 6, like it's maybe there. So have to bear with me when I go to actually do my graphing of this. So you always want to make sure when you're graphing something that you do actually have room. Grab a ruler if you need to extend your axis there. So once I've got my coordinates though, it's just plug in my points. So -2 and 0 is my first point. Then 0 and 2, just like before. 2 and 0 is here. 4 and, oh, I just wrote there, -2 is here. And then 6 and 0. So again, we can really see, and once I connect all these points, it'll really emphasize how the shape of the graph has changed. Okay, so again, this point has now been moved over here. This point has been moved all the way over here. This point is moved this direction. So it's not that it's stretched left or right, it's stretched in both directions from my y-axis. So that's kind of what we're seeing there. Beyond that, things to emphasize, because it kind of looks like it's being vertically pressed down, right? That idea, that analogy of the Play-Doh being that like when we squish it, it kind of oozes out in every direction. So what you need to be conscious of when you're deciding is it a vertical stretch or compression or a horizontal stretch or compression is look for those invariant points. Because like we've now seen between the two examples, that when we have a vertical stretch compression, that's when we're going to see invariant points on our x-axis. And when we do a horizontal stretch or compression, that's when we see y-axis invariant points. Okay, so that's kind of the big thing as to how to tell the difference between the two. Because at first glance, one kind of looks like the other, and that's why people get a little bit confused about that idea when they just look at parabolas, because we don't get the same kind of invariant points. If you're looking at the parent function of a parabola, your invariant point is 0, 0, so it kind of encompasses both of these. So that's where it gets a little tricky. So example 5. We've got y equals f of x and y equals f of 2 of x. Here I would recommend you pause the video, give this one a shot on your own, whether you want to do the mapping notation or just kind of like mentally thinking it through point by point. But I'm going to pause the video now to do mine, so I'm not going to give you a step-by-step blow by blow while I'm doing it. So please give it a shot yourself. So the green is my y1, trying to stick with that color coding theme of orange being just general critical points, pink being, as you can see, my invariant point. So again, we're compressing from both sides, pushing in from the left, pushing in from the right. And it's important to note that the height is not actually changed. So again, that's another thing that you can look for is vertically, are these points staying the same distance apart? And if they are, but the graph looks quote unquote taller, then it's a horizontal compression. So example 6 is another one kind of doing both of the ideas that we just did. Oh, and I should draw your attention. I saw B, and because I've already kind of registered in my head that like whenever I'm affecting my input, kind of seems to have the opposite effect of what the number is. So I am automatically recognized that it was a compression, and then by half, because we always do that 1 over. And again, we saw that in the notes up here. If you need to remind yourself that's how you decide if it's a stretch or compression and by how much, what the factor is, then please make a note of that. So again, give the video a pause, try this one on your own, and then we'll see how you did. Okay, so showing both Y2 and Y1 really emphasizes that focal point where everything is coming together, that invariant point, being conscious again of shape as we're drawing these stretched and compressed functions. I found it pretty easy to draw this sort of parabola-ish shape, but definitely once it was horizontally stretched, I was struggling a little bit more, and you can see that kind of in here. But really make that effort, make it so that it looks rounded if it's supposed to be rounded, make sure it's pointed if it's supposed to be pointed. So combining these, really isn't that different because one affects X and one affects Y. So when we do that, our mapping notation becomes this, so X divided by B and A multiplied by Y. So when I go to tackle an example like this, I'm going to first identify A and B, and I'm going to note that there's a reflection over Y. So you can use mapping notation if you'd like. How I would set that up is, again, choose some critical points. This is a weird graph. I think they're missing that. So I would choose like -2 and 0, and I think that looks kind of like 1.5 for YY value, so 0 and 1.5. And then maybe this is like 2 and 1, or 2 and 2. So those would be the points that I work with. So when I go to fill in my x, f of x versus 2f of -0.5x, that's what I'm going to do. Use those three. And again, you don't need to use a ton of points to be able to recreate a graph if it seems to be following a general trend. It's the weird ones like the piece value ones that we just saw on the previous page that you want to use more points because they're constantly changing directions and they're less predictable. 1.5 and 2 and 2. So when I go to do this, I need to remember that for my x coordinate, I'm dividing by -1/2. So again, reflecting first, so negatives become positives. And 2 divided by 1/2 is actually like multiplying by 2 again. So I would so that gets me 4. I'm then going to multiply my y value by my a value. So 0 times 2 luckily stays 0. And again, that comes back to that idea that any of my x points on my x-intercept are going to come invariant points with respect to vertical. From here, I'm going to go 0 times -0.5, well that, or divided by -0.5 stays 0, but 1.5 times 2 becomes 3. 2 divided by 0.5 becomes 4, but again, remembering that there's that negative, there's that reflection, so I'm going to change my sign as well, and 2 times 2 is 4. So we've got some very, very different points now than we had previously. So when I go to graph this new function, I'm going to use blue again, just because I can. I'm going to go in here, and 4 and 0 is my first one. So 4 and 0, great. And I've got 0 and 3. And even though my coordinate plane doesn't extend that far, I'm going to roughly estimate. It should be about here in my negatives. And so I'm going to go, okay, well, that should be at -4 and +4, which again, I don't have on my vertical axis, but I can guesstimate it'll be roughly there. So roughly here. This is where I'm going to start. It might take me a couple of tries to be happy with my curve. Not quite. So there we go. And that would be my 2f, -0.5x. x. Again, always remembering to name that graph. So again, you could do this mentally. Once I start combining different types of transformations, I usually like to use mapping notation, just a personal preference, but you absolutely don't have to. You do kind of whatever makes the most sense for you and go from there. But there will be practice questions and an assignment on this, so good luck.